finishing the law of Hooke's law, and now we're going to change to motion, because remember this unit was forces and motion. We have some forces, but you have to remember, we saw this, that force is any cause whose effects include either changes in an object state of motion or deformation. We have seen deformation, we have seen the different materials according to how do they deform, and now it's time to study motion. And for that we need some definition. What do we mean by the change in a state of motion? We mean some different things, that all of them are related. We can move something when it is stopped, like for example this wardrobe, when we push it, that's changing the state of motion of this piece of furniture. And we can, if something is already moving, changing the state of motion is making it move faster or move slower, or changing the direction in which they move. Like for example here, when we hit the ball, we are going to change the direction because it was coming this way, and after the hit is going that way. So here we are changing the direction in which they move. This is what we're going to study, but for that we need to first we need to study some definitions. And the first one is reference frame. A reference frame is a point or set of points that we consider fixed. It doesn't have to be fixed, but we are going to consider it fixed for the example that we need to study. In every case, we are going to choose a different reference frame. And well, is the place to which we refer where the objects are. For example, if we are walking in a road, in a path, in the mountain, or but it can also be a highway, we have these signs that are telling us how many kilometers we have walked. And it's also the kilometers in the roads. For example, you can say that's exit 49, and that means that the exit is 49 kilometers away from kilometer zero. That is, maybe you know, it's at Sol. So that's the reference frame for all the roads in Spain, actually, for all the main roads. That's kilometer zero. That's a reference frame, but we can consider any other, like for example the numbers in a street. That's the reference, how we know if we are farther away or closer. And of course in maths we have used the axis x and y, and that's our reference frame, and this is the one that we are going to use a lot in physics. So the axis, and we're going to refer the position to this axis. And the position, of course, is where the objects are. But it's not so obvious because rest and motion depend on the reference frame. And for example, here we have this girl that is saying, I'm standing still, because she's not moving, but the vehicle here is moving. So she is not moving herself, but someone outside is seeing this person moving. So it's not so clear what's the rest and motion. And so for this girl, the reference frame is her floor, for example. And according to that, she is not moving compared to the floor. So she thinks she's standing still. But for her, the reference frame is her own floor, and the vehicle is moving if we compare it to the floor. So it's very important what the reference frame is in every case. Again, from the inside the boxcar, the woman is stationary. It means if we take this boxcar as the reference frame, she is not moving. But if we take it from outside, then she is moving. And here we have more examples. We have person 1, 2, and 3. So now just imagine we're going to think what this person is doing. So for this person, for number 3, he is not moving. No, I mean, for this person, he is moving because she is going to see that this person is farther away. But if we see it from the point of view of number 2, this person is not moving according to him. So because he's keeping the distance, the same distance. So we really need to establish a reference frame every time we want to study rest and motion, because it's not the same. What we have is then that objects move or not depending on the reference frame. That is why we say motion is relative, and everything is relative, as you may know from Einstein and so on. And no reference frame is better than another. Here we have, for example, the Earth. So you can say, no, but I'm not moving. That's a lie, because the Earth is moving around the sun. You know that. And if the Earth is moving, you're moving. So everything is moving, and the sun is also moving, and we're moving around the sun, and the sun is moving around the galaxy. And so really, you have to choose a reference frame for every example you want to work with, and that's okay. But no reference frame is better than any other. So we can say that nothing in the universe is still, everything is moving, because there will always be a reference frame in which an object moves. And that's, relativity, but that comes after, in second of bachillerato. Anyway, so we were talking about position, and we're going to define it as the place where we find an object relative to the origin of the reference frame, because we need, again, the reference frame for everything. So the position is where the objects are relative to that reference frame. So for example, if we have a fly in here, this arrow is the position of this fly. And if the fly moves to a final position, this arrow marks the final position. So the arrows here are representing the position of the object along the way that it follows. But this arrow indicates how far it is and the direction and everything, so it gives a lot of information. And that's why we say the position is a vectorial magnitude also, because you need an arrow to define it, to really give all the information we need with the position. But you will see it in other courses. So here, just know that position is where the objects are, but we need an arrow to represent it. The unit for position is meters, because it's a distance and in the end, and m for meters, you know that. And if the position changes in time, that's how we know that something is moving. If, for example, you start here and you end up here, then something has happened. What has happened? The fly has moved. That's the definition. It seems very obvious now, but it will get more complicated in other courses. So, path. Path is also called trajectory. In Spanish we also always say trayectoria, but in English they use path more, but also trajectory. But we are going to say path all the time. And this is the line, so this is the path, as if you if you understand the word path from a normal life vocabulary, it's the path. So it's the line that the object describes while moving. That's easy, but yeah, we need to define it. And if we, for example, when the fly moves here, if we draw another position and another position, another position, and you join the points of the arrows, you're going to obtain the path, okay, by joining all the positions through which an object in motion travels. But keep this definition that is simple, and this for other courses, but it's the line that describes the object while moving. That is path. And it's important because we classify the movements according to it. If the path is linear, then we say the motion is linear, so linear motion. If the path is a parabola, then we say it's parabolic motion, and it's always when we are shooting something, that's always a parabolic motion. Again, you will see it in first of bachillerato if you're still in science. And if the path is a circle or a circumference, we say it's a circular motion. So it's really important how the path is, the shape it takes. But of course, everything depends on the reference frame, so path also. For example, here, if someone is traveling by bus and you throw something, for the person in the bus, the object is going to fall in like a linear motion. But if you see it from outside, you're going to see that because the bus is moving forward, the ball is going to follow a parabolic motion. And if you don't believe me, I hope you see it here. The first moment is that this is a person that is falling in this bouncing bed, or I don't know how you call this, and it's going to bounce back and so on. But so if you see it from the point of view, from the reference frame of the people standing in here, you're going to think that it follows a linear motion. But when you're outside and you see the track is moving, then you're going to see how it's making a parabola a bit. And then the camera is going to move as well, and then it's a mess, and then you don't know what you're seeing anymore. Of course, your brain tries to stay here because your brain tricks you. That's the thing, you know, and that's why you all like so much optical illusions, because the brain tricks you, and suddenly the brain knows that if you were here, you would see him falling straight. So your brain is going to position itself here. But I hope you can see it a bit and, I don't know, win over your brain. Let's see. So here you see it falling, and now if you focus, you can see that now the camera is moving. But I'm going to put it again so that you can see that while the track is moving, if you see the arrow, you see it's going to move. So here, see, I don't move the arrow, but the person is moving, and that's because this track is moving too. So it's not so obvious. Path depends on the reference frame. Distance travel. That's how it's called in your book, but in other places it's also called path length, and that's really the definition, is the length of the path. So distance you have traveled, and of course this is the distance measured along the path between the initial and the final position, the space. So if we count how many kilometers or meters or whatever unit we want to use, that's the distance traveled, the path length. And of course, because it's a distance, the international system unit is meters, m, and well, that's it. Displacements. This is the shortest distance between the initial position and the final position, and it's not the same as path length, because, for example, if we go from 1 to 3, and this is what we have really done, this is the distance we have really traveled, but the displacement is the shortest distance, so this red line. So it's different. It's also measured in meters because it's a distance, but remember, this is what really happened, and this is this is the path length. This is the path, and if we measure the distance along the path, that's the path length, and this is the displacement, and it follows the same formula. We can Sometimes, I mean, you're going to, if it's going straight, it's the same formula. But yeah, so we're going to use that formula for this one too, because it's going to be the same. But if we, in our example with the displacement and of the fly, so we saw here the path, and if we measure all of these centimeters or whatever she is doing, or it's doing, the fly, that would be the path length. But if we just have one position and the other position, and we subtract them, that's the displacement. So as a summary, here we have the initial position, that's where the fly starts, and it goes up to the final position, and it's for doing some strange movement. That's the path, the trajectory it follows, and it goes from, of course, from the initial position to the final position, and it's the real movement. That's the path. But if we want to say, okay, what's the distance, the shortest one between A and B? That's the straight line. That's not what the object did. That's not what the fly did. But it's the shortest distance between A and B, and that's displacement. And of course, we need the reference frame to measure it all, because if we change the reference frame, everything is going to change. And that's the final slide, because here comes the homework. See you in the next video.